My name's Kyle. I am the former DevRel engineer at FHENIX, and I'm just going to go over FHE 101, kind of an introduction, and then go over a product, which is kind of like a Solana FHE coprocessor, which is the first FHE product on Solana. Obviously, it's a POC work in progress, mostly just for fun. But yeah, so let's start with like what is FHE? So FHE stands for fully homomorphic encryption, which is basically a way to operate over a ciphertext or an encrypted data without having to decrypt it. So think about it as like you can add two numbers. So how data is sent today, this is like what people would really think about end-to-end encryption. Usually when we hear things like certain products are end-to-end, what does this actually mean? Well, it can mean that your device is going to encrypt the information locally, and during the transfer process, it can remain encrypted. However, once it reaches something like a database, a cloud service, whatever you want to call it, the third-party hosting, um, in order for operations, analytics, for this data to be useful, queries, etc., it needs to be decrypted, and then so that the actual logic itself, if you want to think of it as terms of logic or operations, that's what's actually done on these servers. And then it can be re-encrypted and sent back to the device where it is decrypted. And a lot of times that is conflated in our society with end-to-end encryption, but it's kind of a LARP in a way. It's sort of gaslighting, right? Because we obviously see that so many things are supposed to be end-to-end encrypted, but they still get leaked. You get hit with a legal subpoena. There's usually some sort of backdoor to where something can get information. So for better or worse, it's not really encrypted. Uh, and obviously this means data still being stolen. And if you think about it, high level from a cybersecurity perspective, that means that once this data is decrypted at some point in the process, plain text is leaking to memory. And the thing you want to avoid is leaking plain text to memory. So this is kind of how it works by the numbers. This is high level overview of the demand. But to truly to kind of add on to what I was saying, it's basically the ability to operate on data, process it without decrypting it. Obviously, you have things like MPC, which work somewhat similarly. However, these will always have communication overheads, even if you have something like 2P MPC, two-party MPC. So the thing with FHE is that it can be parallelized in a sense because it's not interactive. So these are kind of the two main cryptographic primitives for constructing shared private state. But yeah, again, it might sound kind of like magic in the sense where you can just like have this cryptographic black box of like bits or objects or whatever you're operating on, and you can do that without ever having to decrypt. But it's not necessary. It's just something that can be discovered. A lot of people believe that this will be very useful for things like AI. I'm pretty bullish on this, as I think like privacy and AI is going to be one of the more important things that comes up in the future, especially if you think about the age of automation, where people can scrape your data and essentially create a generalized clone agent, if you would, like a clone with tools that can basically do your job. So FHE is going to be, well, privacy in general is going to be very important in order to protect yourself from this future. Facial recognition is another use case. You have confidential smart contracts, which we'll talk about briefly. These slides are from a company called Zama, which is somewhat similar to the company that I used to work at, FHENIX, in the sense that they're using FHE to add these shared private states to their smart contracts, because by default, those of you familiar with blockchains such as Bitcoin might know that values are usually public. You have things maybe like Monero or Zcash, which could have private balances. However, when you think of, I guess you could call them maybe second generation blockchain, something like Ethereum or Solana, that has like a more robust virtual machine that can handle more complex states, more complex interfacing. But anyways, we'll get to that a little bit in a second. Think about how FHE could potentially change the internet. There's this thesis called HTTPZ, which is like data will be encrypted end to end all the time. That would actually be a very interesting feature. Personally, I think it's sort of just a matter of time. Obviously, adoption is going to come in waves. It's very hard to predict timelines in the future. However, once we see the costs of hardware and all these things come down, it seems more usable. So now let's go over to like a little bit lower level about how FHE actually works. Here's kind of a timeline. So FHE, as we said earlier, is fully homomorphic encryption, but the concept of homomorphic encryption is somewhat different. So you can think of privacy homomorphisms for those of you familiar with the basic homomorphism, sort of like what you do with like, um, function on A, function on B is going to give you the result. Is the same thing if you did it on encrypted, like on an encrypted function, if on A and B to get you C. That's a very jargony way of saying that. Look, if you take the number 2 and 3, you're going to get 5 if you add them, if you do an addition operation, right? However, with FHE, you can encrypt the number 2, you can encrypt the number 3, and then you could do an operation on these encrypted values and have the output value also be encrypted. So the whole thing would be encrypted, quote unquote, end to end. The only thing that you would see is that there is an addition operation that was done on it. However, there are other tools that can theoretically be used to obfuscate this, but those are a little bit more down the line. For now, we're still kind of in the era of bringing FHE to market. But going back to like, for those of you who might be familiar with like RSA, which is a type of homomorphism, and homomorphisms are used in a lot of things, such as like zero knowledge proofs, which is sort of this concept, and a partial homomorphism, without getting too in the weeds here, is basically the ability to do some operations on a ciphertext. So basically, the issue that kind of always came up when in the early days of homomorphic encryption, pre-FHE, if you would, is that when you do these operations on these ciphertexts, like we were just talking about, like let's add 3 to the number 2, what's going to happen here is that eventually you hit a noise threshold, because FHE currently uses something called noisy encryption, which from a high level is a way to obfuscate the truth by kind of adding in noise. It's sort of like bluffing in poker. But anyways, here you can see in 2009, this guy Keg Gentry came up with this idea called bootstrapping, and from there are some other different branches. Today, the two main branches. I guess you could add two main branches. What does that mean? But for example, there's things like TFHE, which is a fast bootstrapping branch, and you have something like CKKS, which is a part of the leveled schemes branch. CKKS is an interesting one because it can be used. You don't have to bootstrap after each operation, and also you have the ability to operate on float versus integers that you would get with something like FHEW or like TFHE. But we've kind of talked about what is FHE, this bootstrapping thing as we were talking about earlier. This is essentially, for example, in schemes like TFHE, and which is one of the types of FHE schemes, can be used from a very high level to sort of kind of make sure that the noise doesn't accumulate too high. Basically, this is a way of making it scalable, so you could theoretically do an infinite amount of operations at any one given ciphertext. Bootstrapped over leveled is sort of what we were talking about earlier. These are kind of things that go into sort of like what specific use case you might use a different scheme for FHE. So Boolean or arithmetic is also another important distinction that's necessary, but we're going to avoid getting too deep into the details here. Obviously, it could be used for things like machine learning that we were talking about before. But yeah, so that's kind of it for the high level overview of kind of just these blog posts that you can check out for yourself. I just wanted to kind of do a quick run through. Now let's kind of run through some simple code. So right here, what we're doing is we're essentially running test on this simple Solana program. So a lot of the major projects that are working right now are using things like are building on the EVM. So if you think about projects like Zama that we were just talking about, they built a product called the FHEVM, which is sort of like using FHE on the EVM. Initially, when this was built, it was built using custom precompiles, which on the EVM is sort of like an endpoint they use to do off-chain computation that can be used in the general VM. But since then has moved to symbolic execution, which is essentially having a collision-resistant pointer on chain that kind of maps towards a server/coprocessor, whatever you want to call it, that sort of actually does the encryption and all this stuff off-chain. And so the basic premise of this Solana program right here is that it essentially will do a similar form of symbolic execution, which means that it's emitting the actual ciphertext pointers that it's storing in the state of the program, versus the off-chain compute, which is done via the Rust server, which we'll walk through. And so this is a pretty simple contract that just does initialization, a quick deposit, a transfer. Obviously, you can see these are the emissions. From there is a very simple listener that's basically going to pick up pick up different events, such as that we see right here in the terminal, where you have the user deposit, the amount. So basically what would happen here is that the amount is going to get encrypted, and we can see this in this server function, which is pretty simple right here, which is basically just running the single encrypt. This is using a U8. If you want to use something like LAMP port values for Solana, you would use something like a 64. Here's like one that's being developed right now. Key generation, as you can see right here, is usually handled by this file right here. So when it comes to FHE from a high level, without getting too into the weeds, there's basically 3 keys that need to be generated. There's a client key, a server key, and a public key. The client key is what's used to actually decrypt. So in more mature FHE ecosystems, you might hear of something called threshold decryption, which is sort of this MPC process of distributing the keys and being able to reconstruct them in order to decrypt. Because obviously, if there's a centralized key, the security of the system can be it's a threat to the integrity. The server key is what you actually are initializing when you're doing the operations in the server. And the public key is basically what's used to encrypt these values. Could be client side, could be anywhere. A lot of projects will use something like a zero knowledge proof to actually verify the plain text encryption. So yeah, these are kind of how the keys are generated using Zama's TF-HERS library. If anyone's interested, I recommend checking it out. And yeah, so basically from there, like we were just walking through the, this is sort of like the one that's being developed right now, but the keys RS, the server, basically is just going to be running these endpoints. This is not a done product, by the way. It's just sort of, kind of a POC, but it's going to add basically the off-chain server here, which we can have in the listener, is basically going to listen to this local Solana node once like the deposit or transaction functions are done. So you would basically pass in the pre-computed pointer, which would require a post request to the server, which would write it to the database, would get that back, and essentially that's your new pointer. So for this case, the deposit is simple because you don't actually need an initial post request before, but the transfer function itself is going to have to require an encryption of the value, and then all the operations that would be necessary would be done in the off-chain server. So what would these off-chain operations include? For example, it could be something as simple as 4 operations as a ternary multiplexer, whatever you want to call it, a selector function, which is basically how you kind of handle branching in FHE, because it operates like constant time code. In the sense where I feel like I like to say that you have conditional assignment, but you don't have conditional write. So basically, you could have an e-bool that could be, this is the second operation that needs to be done here, is the conditional statement, which is basically checking to see that, like, let's say I want to send 5 Solana, but I actually only have 4. So I have to make sure that I'm sending a valid transaction here. So basically, if I am meeting the correct requirement, then it is going to quote unquote branch. It's going to select either ciphertext A or ciphertext B, which in this case would be the initial value put in, or 0 because it's not valid. From there, you would basically need to do 1 addition and 1 subtraction operation from the receiver and the sender, respectively. So yeah, that is, if that makes sense. So basically, the high level flow is run Solana local node right here, and then run the Solana tests, which are basically going to spoof what everything is going to be done, spoof the on-chain logic. Those events are going to be picked up by the listener, and then those are going to be forwarded to the Rust server that will actually handle the computation. And depending on what is actually being emitted, certain callback functions will be necessary for certain client-side resealing. So yeah, that's high level, basically a cool walkthrough. If anyone's interested in learning more about FHE, I would check out projects like FHENIX or Zama. Or if you're interested in potentially exploring FHE on Solana, feel free to hit me up. Very much work in progress. But yeah, that's it. So thank you for your time.